We present OSTEC, One-Shot Texture Completion, which proposes an optimization-based approach to complete missing 3D texture from a 2D face image. The last few years have witnessed the success of nonlinear generative models in synthesizing high-quality images. Many recent 3D facial texture reconstruction and pose manipulation approaches still rely on large and clean face datasets, yet the collection of such datasets is still very costly. In this work, we propose an unsupervised approach for one-shot 3D facial texture completion that does not require large-scale texture datasets, but rather harnesses the knowledge stored in 2D face generators. The proposed approach rotates an input image in 3D and fill in the unseen regions by reconstructing the rotated image in a 2D face generator based on the visible parts. The problem of predicting the missing color in 3D texture or predicting a new view from a single image has been the application domain of many machine learning algorithms, starting from simple nearest neighbor interpolation or using linear statistical priors to modern deep learning regression techniques. The problem has been modeled as fully supervised, such as training with pairs of missing and complete 3D facial texture, or using self-supervised methods and image rendering. Nevertheless, fully supervised or self-supervised, to the best of our knowledge, all current models belong in the family of regression techniques. Contrary to them, we take a radically different line of work in this study. We propose to rethink the 3D facial texture prediction and rotation generation as an optimization problem, and design our method as a one-shot texture completion approach. Our approach capitalizes on the power of 2D face generators to recover the unseen part of a face image by 3D rotation. Our method starts by running an off-the-shelf 3D face reconstruction method for an input image, and then the available texture is interpolated to a UV space by nearest neighbor sampling. In order to fill in the less visible parts of the texture acquired from the original image, we rotate and render the fitted mesh by certain angles that maintain best visibility of every part of the face with a near perpendicular view. For each perspective, we extract a visibility UV map ranging from -1 to 1, indicating the angles between the triangles and camera. Each of the novel perspectives dominates certain part of the texture map in terms of clarity and visibility. For each of the rotated faces, we recover the unseen regions by projecting the visible parts to a 2D face generator as an appearance model. The projection is initialized by an encoder network and performed by an iterative optimization process that is restricted to the visible regions and the recovered texture from the previous camera angles. And it is guided by energy terms such as identity loss, perceptual loss, landmark loss, photometric loss, etc. In order to generate globally consistent texture maps, we run the optimization for various camera views progressively, meaning that after every optimization, we stitch the generated UV maps into the current UV map at its dominant regions. The UV maps are stitched by alpha blending and RGB normalization. Finally, we render it once more by a frontal perspective and perform a final projection for frontalization. As a byproduct of our approach, we built a 3D texture model by completing texture view maps for around 1500 images without any 3D data collection. Here you see some textures from the dataset and the resulting texture model. In these figures, we illustrate qualitative performance in comparison with other methods for UV completion, frontalization, and 3D texture reconstruction. We also conduct an ablation study to demonstrate that each of the energy terms has significant contribution to the final output. Moreover, we quantitatively show that our approach outperforms other state-of-the-art methods for face frontalization and texture completion tasks. Thank you for listening. In the rest of the video, we will show more results from CFP dataset for texture completion, frontalization, as well as their cosine similarity scores. Enjoy!